Welcome to Module 3. In Module 2 we built the three pillars, facts, rules, and queries, and we used them, but we treated the reasoning engine as a black box. Today we open that box. Behind every Prolog answer are two mechanisms working together: unification, which decides whether a goal matches a clause and binds variables in the process, and backtracking, which is how Prolog searches when a choice leads to a dead end. Together they form an algorithm called SLD-resolution. By the end you will be able to read any Prolog computation as a search. Here is the plan. We start with unification, the matching operation at the heart of Prolog, and the table of cases that tells you when two terms unify and what bindings result. Then we turn to search, choice points, backtracking as depth-first search, and the formal procedure, SLD-resolution, that ties it together. We finish with the centerpiece of this module, a fully traced compound query, shown both as a step-by-step trace and as a search tree, so you can actually watch Prolog think. Every step Prolog takes is one of two moves. First, it tries to unify the current goal with the head of a clause. If they unify, it adopts the resulting variable bindings and continues with the clause's body. Second, whenever a goal fails, or whenever you ask for another answer, it backtracks. It rewinds to the most recent point where an untried alternative remained, and tries that instead. Unify, and on failure backtrack, repeated until the goal succeeds or every alternative is exhausted. The formal name for this strategy is SLD-resolution. Unification is the process of making two terms identical by choosing values for their variables. It is what the equals sign means in Prolog. The query x equals Mary does not assign Mary to x the way an imperative language would. It asks Prolog to find bindings that make the two sides the same term. If such bindings exist, unification succeeds and the variables are bound. If no bindings can make the terms equal, unification fails. Every goal you pose is answered by unifying it against the clauses in your program. These 6 cases cover everything you need. Two identical ground terms unify trivially. A variable against a constant binds the variable, so x against Ian gives x equals Ian. Two variables against two constants bind both at once. Two different constants never unify. Ian and Pete simply clash. A repeated variable must take a single consistent value, so x against x cannot match Ian against Lucy. And structured terms unify position by position. F of x and b against f of a and y binds x to a and y to b. Read this table until each row feels obvious. The table follows from 3 rules. A constant unifies only with an identical constant. A variable unifies with anything, and becomes bound to it. And a compound term unifies with another compound term only when they share the same functor and the same arity, and every corresponding argument unifies in turn, recursively, all the way down. One more thing to remember: within a single solution a variable, once bound, stays bound. Prolog will not quietly rebind it to make a later goal succeed. Bindings live inside one attempt at a solution. If the same variable appears twice in a goal, both occurrences must end up equal. That is why parent of x fails against parent of Ian, Lucy. And each time Prolog uses a clause, it takes a fresh copy of that clause's variables, so the x in one rule has nothing to do with the x in another. When Prolog backtracks, it undoes the bindings it made along the way, returning variables to unbound, so the next alternative starts clean. Binding and unbinding is the bookkeeping that makes search possible. Now the search. When a goal cannot be satisfied, Prolog does not give up, it backtracks. It returns to the most recent choice point, undoes the bindings made since, and tries the next alternative there. This is exactly depth-first search. Go as deep as you can down one path, and when it dead ends, rewind to the last fork and take the next branch. Think of walking a maze with one hand on the wall, down a corridor, hit a dead end, back up to the last junction, try the next opening. Prolog explores your clauses the same way. A choice point is any place where more than one clause could match the current goal. Ask parent of Lou, y, and there are two matching facts, so Prolog records a choice point. It returns y equals Pete first, and remembers that Pauline is still untried. Press semicolon and it backtracks to that choice point and delivers y equals Pauline. Choice points are where alternatives are stored, backtracking is the act of returning to them. When no choice points are left, there are no more answers, Prolog reports false and stops. Put together, the procedure has a name, SLD-resolution, selective linear definite clause resolution. The recipe is short. Select the leftmost subgoal. Find a clause whose head unifies with it. Apply the resulting substitution, and replace the subgoal with that clause's body. Recurse on the new list of subgoals. And whenever a subgoal cannot be resolved, backtrack to the last choice point and try the next clause. Success is reaching the empty goal, failure is exhausting every clause. That is the whole engine, in 5 steps. Let us trace a real one. The query asks for an X who is a parent of Lucy and also a parent of Peter, written parent of X, Lucy, then parent of X, Peter. Prolog takes the first goal and walks the facts in order. Lou and Pete, Lucy is not Pete, fail. It keeps going past Pauline, past Ian and Peter, none make Lucy the second argument, until it reaches parent of Ian, Lucy and binds X to Ian. Now it carries that binding to the second goal, parent of Ian, Peter, which is a fact, so it succeeds. The answer is X equals Ian, found by unifying each fact and backtracking past every miss. The same computation has a shape, a search tree. The root is the query, each fact Prolog tries for the first goal is a branch from it. 5 of those branches die immediately, marked with a cross, because Lucy does not match. One branch, parent of Ian, Lucy, succeeds, binds X to Ian, and grows a child for the second goal, which also succeeds and reaches a checkmark. Depth first search is simply the order in which Prolog visits this tree, left to right, top to bottom, retreating up the moment a branch fails. Every Prolog query, however complex, unfolds as exactly this kind of tree. With unification and backtracking in hand, you can now read any execution. When the same predicate has several clauses, expect choice points, and be ready for more than one answer. When a goal fails, look back to the last choice point, that is where Prolog resumes, not at the top of the program. And remember that the order of your facts and clauses fixes the order in which answers appear. The engine is fully deterministic, the apparent magic is just disciplined search over the clauses you wrote. To summarize, unification matches a goal to a clause and binds variables to make them agree, governed by 3 simple rules and the 6-row table. Backtracking is depth-first search over choice points, undoing bindings as it retreats. And SLD-resolution is the loop that combines them, select, unify, replace, recurse, and backtrack on failure. Next, in Module 4, we put this engine to its most powerful use, recursion, defining relationships of unbounded depth, and watching the very same unification and backtracking carry a definition all the way down to its base case.